The Research and Development Department of an automobile manufacturer has determined that when a driver is required to stop quickly to avoid an accident, the distance in feet the car is traveling during the driver's reaction time is given by R of x equals 3/4 x, where x is the speed of the car in miles per hour. So here we've got the speed of the car in miles per hour. 3/4 of that is going to give us a number, and that represents the number of feet based off of the reaction time of the person. There's a little bit of reaction time when there's going to be an accident. We can go ahead and graph this. The axes we're going to represent here are, of course, speed in miles per hour. This is the variable x. And over here, distance traveled in feet. And again, we're talking about 3/4. So if they were going 20 miles per hour, 3/4 of 20 is 15. Okay, 15 would be about here. It would be about that much. We could do that a couple of times. 2 points determine a line, so we could do that, and we could get ourselves a line. And here is the line that represents that particular relationship. But now, of course, that doesn't give the total time for stopping. That's just the distance traveled based off of the reaction time. There's another part to this. So then the distance in feet traveled while the driver is braking is given by this. So then this b of x represents the feet traveled while braking. The x still represents miles per hour. This is a parabolic, a quadratic relationship. 1/15 of x squared. So whatever their speed is in miles per hour squared, a 15th of that would then represent the number of feet required for braking. So if you're traveling faster, the distance in feet required for braking is, of course, going to be a bigger number. Let's go ahead and put that graph. This is going to be a parabola. And there it is. Now the question here that is being asked in this problem is the overall distance, or the total distance. It's going to be a combination of how long it took for the driver to react, plus the amount of distance that is covered while they're braking. This is a composition of functions. So the rest of the problem says this: find the function that represents the total stopping distance t. Graph all three of them. I've actually already graphed the first two. We're also going to graph the total stopping distance t of x. And this represents a car traveling between 0 and 60 miles per hour. To get t of x, we have to do a composition of functions. In this case, just a simple addition of functions. We're going to add this function to this function. So like that. Go ahead and substitute the numbers in. Here is our function. This now is the total stopping distance in feet at a given miles per hour of the car. This term represents, of course, the reaction time. This term represents the braking. So we go ahead and graph that one. And again, it's a parabola, which should not surprise us because we have a squared term. This is a quadratic equation. So we've got that parabolic shape to it. And this graph then gives us that. So at any speed, say 40 miles per hour, we could then read over here our y value that would tell us the amount of feet required to actually stop when we put together both the reaction time and the braking time.